Hello guys, welcome to the channel. Today I have an absolutely cracking integral, so let's just dive straight into it. And just before we start, actually, I just wanted to give a quick update that from tomorrow I'm going to have school, as you do. And so that means I'm not going to be able to upload videos every day because I just won't have that time. I'm going to experiment with some stuff, but I think I'm going to try upload twice a week because I really do enjoy this, but unfortunately I don't have the time. So I'm going to be doing two different things. I'm going to be doing unique integrals as normal, so integrals like this because I think they're quite fun and they really test your understanding and you see new tricks. And then I'm going to start a new series, which I'm calling A Young Person's Guide to Calculus. And it's just going to be kind of more educational or developing knowledge kind of thing. So, like differentiation, integration. Um, I'll start off, I guess, with like A level stuff. And then once I learn and then go into like more depth and go into more fun tricks and stuff. Um, but that's going to be something that starts. So there'll be a bit of balance of understanding as well as knowledge. But I do want to quickly also say that maths is timeless. So even though I won't be uploading every day, as long as you're finding you can still find an integral every day to try, and including this channel as well. Whether it's uploaded an hour ago or a week ago, it's all just as good practice, and it will always be just as good practice. So yeah, so let's just dive straight into the problem. So here's the problem, and I actually prepared a hint, so I'm just going to pause for a moment for anyone who wants to try the integral without the hint. Cool. So the hint I prepared, and it's always a good go-to in these situations, is to write everything in terms of sine and cos. So I'm just going to pause for another moment for anyone who wants to try with the hint. Cool. So let's dive straight into it. So here's the problem, and as the hint suggested, it's good to write things in terms of sine and cos. It's always a good starting point, especially since we have so many functions and so much going on, and it's all kind of cluttered. So it's always good to write in terms of sine and cos when you don't know what's going on, just so you can try and simplify and see if there's any patterns. So I'll start off with the secant. Secant is just 1 over cos, so just writing 1 over cos and remembering our powers, just like so. And then cot is the same as 1 over tan, and tan is sine over cos, so it's just going to be cos over sine, and cosecant is just 1 over sine, so just like that, cos over sine, again remembering powers, and here 1 over sine. And now we have fractions divided by fractions, so now it'd be really good to just simplify and write it as one fraction, just like so. Just knowing when you have something divided by 1 over sine, it's the same as multiplying by sine, so that's why that sign jumps up. And yeah, just being careful with our fractions, what's being divided and what's being multiplied. But you get this guy. And then there's a really nice spot, which is you can factor out sine cubed x over cos to the 9x, just like so. And you're left with 1 minus cos squared x, because here there's 2 less. It's cos to the 7, not cos to the 9. So you're left with cos squared x to factor out. And then you can use the identity cos squared x plus sine squared x equals 1. And if you rearrange it to make sine squared x a subject, you can then sub out 1 minus cos squared x plus sine squared x. Cool. And then it's just a matter of simplifying, just like so, to get sine to the 5x over cos to the 9x dx. And definitely our job's not finished, but we can see we're definitely heading in the right direction, because now everything looks a lot more simple, and we just have it as one simple fraction, and it's a lot easier to work with. From here, there's a really nice trick or a really nice find, which is if you write everything in terms of tan and secant, just like so. So what I've done is I've just have sine to the 5x, because tan is sine over cos, and then I've split this cos to the 9x into cos to the 5x times cos to the 4x on the denominator. So then the cos to the 5x will go with the sine to the 5x to produce tan to the 5x, and then the cos to the 4x, I'm just going to write it as secant to the 4x, because that's just what it is. And then from here, what I'm going to do, it's going to look quite funny, but there's a nice trick, a nice spot. I'm just going to write secant to the 4x as secant squared x times secant squared x. And you're going to see why as I work through this. Firstly, I'm going to look to try and sub out one of these secant squared x's for something else. So I have here our identity, cos squared x plus sine squared x equals 1. And if I divide the left-hand side and right-hand side by cos squared x, just like so, will simplify. This will simplify to 1, and this will be tan squared, and this will be secant squared. So we can clearly see that secant squared x is equal to 1 plus tan squared x, and we have secant squared x here. So it's just a matter of subbing it out, 1 plus tan squared x. And we're going to keep the secant squared x here deliberately, and we're going to see why in a moment. And then what we can do, or what we're going to do now is we're just going to expand this out and expand the tans out, so we have it like this. There you go. And so now what we're going to do, and we've put in this specific form to try and take advantage of the fact that if you differentiate tan x, you're going to get secant squared x. And of course, integrating is just a reverse of differentiating. And so it really means now that we've set everything up perfectly for a nice substitution. So a good substitution is as simple as just using u equals tan x. And whenever we have a new variable, we should chuck a box around it so we remember. And if we differentiate du over dx is equal to secant squared x, and if we make dx a subject just like so, now what we can do is we can sub out dx for du over secant squared x, just like that. And this is now really promising, really good, because now the secant squared x's will cancel out just like so. And that's amazing now. And we're just left with this guy. Now, but we have it in respect to u and in terms of x. So now we should sub out the tan x's for u, just like so. And now we have this integral. And since there's no bounds, it's just a general solution. We've successfully done our substitution because it's in terms of u in respect to u. So from here now it's just a matter of integrating, and we can use this rule, which is just integrating polynomials to produce this result. And now if we call back on our substitution u equals tan x, we can now sub tan x back in for u because we are looking for our answer in terms of x, not in terms of u, just like so. And then the final thing is to write it out and expand it out and to add the plus c because it's a general solution. So it's important not to forget that plus c. And there's your answer. So you can chuck a box around it. That's quite an integral. I really do hope you enjoyed the video, and I look forward to seeing you guys next time.